All right. So, looking ahead to our reminders, we do have an individual quiz today. There is a Mastering Chemistry homework set due tonight. It should be over the rest of Chapter 10, so some Vesper and some what we're going to do today, Polarity. What else? Exam 2 is a week from today, which covers everything since the last exam, pretty much. Whatever chapters those are, is that 7, 8, 9, 10? Yeah. Should be all those. What else? There is a bio seminar tomorrow at 11 o'clock in here. And then there is a Cheminar November 1st at 2 o'clock in here. I think there's a math seminar coming up too. I should know the date and time for that.
Does that count?
It does. Mm-hmm. Anything in the natural sciences. So math, physics, chemistry, biology, and science.
Well, the malaria stuff.
A smidge. It won't be the majority of the material. It'll just be a little question or two about molarity.
Can you repeat the chapters in so?
It should be over. Let me double check my syllabus. If I found the right page of my syllabus. Should be all of 7, 8, 9, 10, and a little bit of 4, because we didn't quite finish 4 before the last test,
Yeah.
with like the very end of like limiting reagents, things like that. But the majority of the material. Yep. Yeah. So the majority of the material is going to be over 7, 8, 9, 10, which is all periodic properties, bonding, low stat structures. Yeah. Mm-mm. No. The only Mastering Chemistry is due tonight, and it's over Chapter 10. My plan is we're going to finish Chapter 10, the majority of it today. We're going to wrap up whatever we don't finish on Wednesday. Talk about some new material that won't be on the test, that kind of pulls it all together about molecular attractions. And then Friday we'll just review for the test, do some practice problems. All right. So where we left off, last time we did a whole bunch of practicing with Vesper structures. So why do we care what the shape of the molecule is in 3 dimensions? It's because how it appears in 3 dimensions affects how it's able to interact with other molecules. So in most dot structures, covalent bonds look like the electrons are shared equally, but that is not always the case. So let's look at the difference between HF and hydrogen gas. So let's draw HF first. How many electrons does hydrogen bring to the Lewis dot structure? Okay, and then how many does fluorine bring? Okay, so it would look something like that. If I were to draw it as a model like that, where it looks like that one shared electron is now a stick. Everybody's good with that? Good. It would appear, based on my drawing, that the electrons are being shared equally. What do we know about HF that would make that statement untrue? Firstly, is this compound going to be ionic or molecular? We'll go to the periodic table. Okay. Hydrogen's on this side of the table. Fluorine's on this side. So what does that tell you about its ionic or molecularness? Should be ionic because they're on opposite sides of the table. It's a metal bonding to a nonmetal. So HF should be ionic. Second piece of evidence that may not be the right drawing is How electronegative is fluorine? Super, right? It is the most electronegative. What does that mean about its desires for electrons? It wants electrons or it's willing to give them away? It strongly wants those electrons. So even if you weren't sure if it was ionic or molecular, fluorine's the most electronegative, which means it desperately is seeking electrons. So it is more appropriate to say this. From electronegativity, we know that the fluorine wants electrons and hydrogen is willing to give them up. That'd be true based on what we just said about electronegativity. Fluorine wants the electrons, hydrogen is willing to give them up. So, based on my bond, is my bond, it looks like it's equally sharing. Is it in reality equally sharing? No. Where are those electrons more likely to be? Around the fluorine or around the hydrogen? They're more likely to be around the fluorine. If they're more likely to be around the fluorine, what charge would that fluorine have? -1. How we draw that is as such. So, what does it mean from those people who have taken math? If it's a big triangle, what is the letter that or the word that we call a big triangle? Delta. Big delta. What does delta mean? Change in. This is little delta, so it means little change. So big delta means big overall change. It usually means subtraction. This is little delta, and it tells us there's a little change. That this hydrogen is more positive than what you would think it would be, and this fluorine's more negative than what it would think it would be. So it's a little change. We haven't broken the bond. We're just saying this one's more likely to be on the positive side, that one's more likely to be on the negative side. The other thing we draw is something that looks like this. It looks like a plus sign with an arrow shooting out of it. The plus sign goes on the atom that is more positive. The arrow shows you the directions that the electrons are heading. This tells us that's a polar molecule. And we call it polar because it now has two poles, right? You can think about like a magnet or something. There's a positive end and a negative end. So all of my sketches are showing the same thing. There's a positive side and a minus side, and it's overall polar. Yeah, sorry, I don't know why it's looking crazy. That should be polar molecule. Ooh, that's a little better. All right. So that was this guy. Let's take a look at hydrogen. This H2. All right, looking at H2, let's walk ourselves through the same argument and see if they are similar or they are different. So it would appear, based on my sketch, right, that these electrons are being equally shared. Based on the electronegativity, are they the same electronegativity or different electronegativities? They are the same electronegativity. If they are the same electronegativity, is one H more likely to have the electrons around it than the other? No, they are equally likely to have the electrons around them. So can I draw anything that looks like this for, I can't. If I cannot draw something like that, good guess as to what kind of molecule this is. What would I call it? nonpolar. So either you're polar or you're nonpolar. This guy is nonpolar. Because I cannot draw two poles to the molecule. Questions on that? Makes sense mostly. Okay. So that's easy if it's just two atoms, right? What if there's more than two atoms, which would be a polyatomic molecule? So a polyatomic molecule that may have a polar bond may not be overall polar. So in these cases, right, there's only one bond. If there's only one bond and that bond is polar, the molecule is polar. In this case, I have a molecule with more than one bond, some of which may be polar, but we're going to have to look at all the bonds to figure out if it's actually polar overall. So, let's take a look at carbon dioxide. All right, carbon dioxide, which atom do I put in the center, the carbon or the oxygen? Carbon. Why do I put carbon in the middle? Yeah, less electronegative, so carbon goes in the center. Good. Is my carbon happy at this point, or do I need to do something else to it? Am I done drawing my molecule? No. How many more electrons does carbon need to be happy? Needs 4 more. Okay. How's that? That look pretty good? Everybody happy? Oxygen's good? Carbon's good? Good. Okay. So question 1, are these bonds polar? Let's go to the periodic table. Are they of equal electronegativity? No. Which atom is more electronegative, the carbon or the oxygen, looking at just that bond? Oxygen. So which direction should I draw my arrow? To the oxygen or to the carbon? To the oxygen, okay? And I'll do the same thing down here. All right, so I got 2 bonds, each being pulled in 2 different directions. So yes, the bonds are polar. Both are polar. So now the question is, what is the molecular geometry of this atom? How many electronic groups are surrounding my central atom? There are 2 electronic groups. What do I call if it's 2 electronic groups, none of which are lone pairs? Linear. Good. If it's linear, do I have to change the way I've drawn it at all? No, right? I drew it linear, so that's good. So the third question is there an overall dipole moment? Well, let's take a brief pause and define what a dipole moment is. So a dipole moment is really what you drew here in this arrow. So a dipole moment is a way to explain it. It may not be the most articulate. So dipole moment is the net direction that the polar bond is pulling. So in this case, there are two competing dipole moments. Right, we have one bond going to the left. We got one bond going to the right. So the question is there an overall direction, or are they canceling each other out? They are canceling each other out. So the answer to 3 is no. There is no overall dipole moment, because while there are two polar bonds, they're pulling in opposite directions. So there is no overall. Good on that. Fairly clear. All right, let's take a look then at water and ask the same set of questions. All right, so looking at water, we've done the picture of water a bunch of times. I'm going to ask them in a slightly different order because I think it'll make more sense if we do the geometry first and answer the other question. So 1, so how many electronic groups are around my oxygen? 4. How many of them are lone pairs? 2. So if I want the electronic geometry, which just looks at how many total, if there's 4 total, what's that called? Tetrahedral. Do we have a tetrahedral? Not really, because it's 2 and 2. So what is the more appropriate name for 2 and 2? Bent, my favorite. Just a funny word. Like pants. I think pants is the funniest word for no good reason, because the more you say it, the crazier the word sounds. I'm sure that happens to everybody. Like when you're saying a word and you're like, that can't be right, and the more you say it, you're like, no, that's definitely wrong. But then it turns out you're right. It's just you've said it so many times that it sounds ridiculous. Pick a word later today, try it a bunch of times. You'll find it's true. True. All right, so if actually it's bent, what is the more appropriate way to draw this? It's going to look more something like this. With my little lone pair Mickey Mouse ears. Okay. So, second question. Are there polar bonds? Yes. Which direction on my covalent bond is the polar direction? Towards the oxygen or towards the proton? Towards the H. Towards the oxygen, okay? Now that we have lone pairs, we also have to consider where the lone pairs are pulling. So, lone pairs are even more electronegative than any atom. So if you're thinking of your periodic table, fluorine, the most electronegative atom, lone pairs, more electronegative than fluorine. That helps you think about its scale. So if lone pairs are more electronegative, which direction are they going? Towards the oxygen, like they want to be closer to that, or they want to be farther away? Farther away. That makes sense on a few different levels. Electronegativity, or I think about the fact that the lone pairs need a lot of space, and they'll be happier if they push away from the oxygen rather than be pulled in closer to it. Both those arguments work. So, question 3. So the answer to that is E. Bent. Yes. Is this overall a polar molecule? So do the polar arrows cancel each other out? No. If they don't cancel, then it is a polar molecule with polar bonds. Okay, let's do another one. Just to have a good set. How about we look at, what's a good example? I have it right here. Let's do CH3Cl. Okay, so this, is that pretty good looking? It's not bad, not bad. I don't think I made mistakes on that. Okay, so what would be the molecular geometry? Tetrahedral. Good. Are the bonds polar? Yes, but they are a variety of polarities. All right, let's do the carbon, hydrogen ones first. Looking at carbon and hydrogen, which one's more electronegative? Carbon. So which direction should the arrow be pointing? To the carbon or to the H? Okay. All right, what about the carbon chlorine? It needs to go towards the chlorine because chlorine's more electronegative than carbon. So yes, there's polar bonds. Do they cancel each other out, or is this molecule polar? It is polar. This is a polar molecule. What if I changed this chlorine to hydrogen and made it CH4? Would it then be polar or nonpolar? Nonpolar, correct, because they all would be canceling each other out. How do I feel about that? Pretty good, pretty straightforward. That's the majority of what's on your homework tonight, being able to draw it and figure out which direction is being pulled the most. So which direction are these little baby arrows in, and then do they cancel each other out? Good? Okay, so then let's talk about, oh, this is my summary sheet. Draw the Lewis dot structure, determine the VSEPR shape, determine if there's any polar bonds, determine if the polar bonds make a net dipole moment or if they cancel each other out. These are just some extra ones that you can do on your own just to work your way through, just some practice problems. All right, so then we have polar, covalent, and ionic molecules. So all three of these types of molecules have a different distribution of electrons around it. And because they have a different distribution of electrons around the bonds and atoms, they must have different properties. So polar, like we just talked about, is the unsymmetrical distribution of electrons. There is definitely a direction that the bonds are being pulled in. Nonpolar is where it's all symmetrical and everything all cancels out. Ionic is the complete transfer of electrons from one atom to the other. So that's when we're looking at, like, what's a good example? KBr. something like that, where you have like the charges and they equal 0. So in this case, the bromine's taken all of them, left the potassium with none. Good. So different properties come from these different distributions. We just saw that water is a polar molecule. As a property of polar molecules, polar molecules choose to interact strongly with each other, right? Because you can think about them as like mini magnets, that they all line up real nicely, positive and minus, and end to end, so they interact real strongly. But they do not want to interact with nonpolar molecules. So things that do not have an overall charge do not interact well with things that do have a charge. How well do nonpolars interact with other nonpolars? Really, really well. So that's another nonpolar molecules. Nonpolars interact strongly with each other. And you have seen this a bunch of times, you just haven't called it that. So water is a great example of a polar molecule. What is the one thing you say, water and this thing never mix? Oil. Oil's nonpolar. Turns out that's why they can't interact. They do not interact with each other well at all. So this polar, nonpolar, a polar ionic, nonpolar ionic, any combination of those. Are called intermolecular forces. So based on your Lewis dot structure, you can then figure out your VSEPR structure. Based on your VSEPR structure, you can figure out your polarity. Based on your polarity, you can make a good hypothesis as to how two molecules will interact with each other. Let me see how many main ways. I think it's 1, 2. There's going to be 4 main ways that molecules interact with each other. There's going to be dispersion forces, which is the weakest of all interactions. You could have a dipole-dipole interaction. What is the requirement, do you think, based on the name, of the molecule to be able to participate in a dipole-dipole interaction? They both have to be polar. Good. The third, that's what I want to do then. Go to this. You can have an ion-dipole interaction. What kinds of molecules do you think participate in ion-dipole interactions? Ions and dipoles, perfect, ions and polars. Just checking, make sure everybody's conscious. And the last one, which is going to be a special case, is called hydrogen bonding, which is a misnomer because there's no bonds. It does involve a hydrogen, but there's no bonding. It's a force, not a bond. Whoever decided to name it decided to do it confusingly. It's not a bond. Any guesses on what has to be involved in a hydrogen quote-unquote bond? Hydrogen. It's going to be one hydrogen. How do I want to say this? So it has to be between two polar molecules, one of which has to have the proton, and the other one has to contain a nitrogen, an oxygen, or fluorine. Why would it be those three? Out of all the atoms, what did those three things have in common? They are super, super electronegative, which means that they're going to really pull on this proton on the other molecule. They're going to try and rip it off. That's why it seems like a bond, because it's such a strong interaction that it's much stronger than just a dipole-dipole to level up from that. Okay. We'll do this. This will be the last thing we do today. And then Wednesday, you have your quiz. We'll do this quiz. Wednesday, if you're bringing the PowerPoints to class or you're looking at them online, bring the chapter 11 ones. Because the last few things I want to talk about, these interactions, is really in chapter 11. Just a few things in that chapter, which we'll come back to later. It's a weird chapter. It has a little bit of this, a little bit of that. So if you're bringing the PowerPoints, just bring chapter 11. All right, so the last thing about classifications of bonds, and then we'll talk more about interactions between these types of molecules on Wednesday, is that the classification of bonds, so if you're not sure if it's polar or not polar, it's the exact argument we walked through a few minutes ago. We look at the electronegativity for each bond and see how big of a difference it is. If it's zero difference, what does that most likely tell you about the two atoms involved? They're the same, right? If there's two atoms of the same type, 0. If it is a huge difference, greater than 2, it's most likely ionic, because you're probably crossing sides of the periodic table. Like that potassium bromide we just looked at, going to be ionic because we've gone across the entire periodic table. If it's somewhere in the middle, between 0 and less than 2, it is most likely a polar bond. So, yeah, that's if there was a periodic table, which is right here, a periodic table. Increasing differences in electronegativity. Go that way. So here's my example. Let's look at, it's on the next page if you have your PowerPoints. On the next page, there we go. Specify the following bonds as ionic, polar, covalent, or covalent. So the bond in a cesium chloride, a bond in a sulfur dihydrogen, or the bond in this crazy, crazy molecule. So all you're going to do is subtract them. Doesn't even really matter what the molecule looks like, because I'm just looking at the bond in there. So cesium, let's see if I can find cesium. Oh, it's all the way down here. Cesium and chloride. Best guess without doing subtraction, ionic, not ionic. Cesium, chloride. Probably going to be ionic. So I'm looking at this bond right here. So I do 3.0 minus 0.7. What is that? 2.3? Based on your table, is that ionic? Not ionic? Greater than 2, so it's ionic. True. All right, then we do this one. Okay, if that's 0.4, where does that fall on our table? Everyone's so mesmerized by my amazing subtraction skills. Covalent, polar covalent. Without even looking, if I want to know what's going on between two atoms that are identical, what should that be without even doing subtraction? Should just be plain covalent. All right, questions on that? That's what you're pretty much going to do on your homework. Look at those types of bonds, then draw it. All right. In that case, today is individual quiz day. Yay! Let's see what we need. You don't need anything but a pencil. So good. And I have the group quizzes from Friday passed out also before you leave. So make sure someone from your group gets it before you leave. And I'll cover Pura too.